Thank you for the introduction, the invitation. Yes, this is what I will be talking about today, about counting pseudoholomorphic curves. And let me outline the talk. First, I will start with talking about counting pseudoholomorphic curves in general, so we frame it as Gromov-Witten theory. Pseudoholomorphic curves with boundary fall into a variation, I guess, of that theory, which we call open Gromov-Witten theory. Open in the sense that it's not closed, so we do have boundary. So that's the terminology. I blame physicists. Next, so I'll talk about the definition and like an introductory, like what it is that we want to count and how we might want to approach the question. Then I will talk about WDV equations in closed theory and in open theory, and those equations have to do with calculations, among other things that they do. And hopefully, if time permits, we're also going to talk about another aspect of those WDV equations, which is a quantum product, again, in closed theory, and then the analog in open theory. So let me start with closed Gromov-Witten theory. And throughout this talk, when I say Gromov-Witten theory, I only talk about genus 0. There is highly non-trivial theory in higher genera, but I'm not doing that today. My universe is a symplectic manifold, so it's just an even-dimensional manifold with a two-dimensional volume, notion of two-dimensional volume. To the symplectic manifold, I attach an almost complex structure. So you can think of any, say, Kähler manifold would be an example of that. A special baby example I want you to keep in mind is the projective space, CPN. I will also point out that I'm super nervous right now, so if you ask questions, that will really help. So please do.
What's omega Fs?
Fubini Studi, the Fubini Studi metric. Thank you. Okay, so a baby example I want you to keep in mind is the projective space. And the basic objects we want to deal with in this Gromov-Witten theory is maps. So we have a sphere here, which is a genus 0 Riemann surface. And it's, in particular, a complex manifold. We have the target manifold X, and it has a complex or an almost complex structure on it. We want to answer the question how many holomorphic maps or pseudo-holomorphic maps there are from a sphere to the ambient manifold. Now, naturally, as put right now, this is not a question that has a concrete answer because well, for starters, there's no reason to assume that the answer is a finite number. So we'll have to impose a bunch of conditions. First of all, we need to fix the degree of the map, right? Which which homology class it represents. And we'll also need to impose further conditions, so we will put marked points on the sphere and tell you where those marked points need to go. So we'll fix submanifolds, if you will, of the target manifold, and we require the marked points to be mapped into those submanifolds. And yeah, I drew them as just squiggly lines, but as a schematic description, obviously you might want to take all kinds of submanifolds of various dimensions. And if you cook up the dimensions properly, you should be getting a question with a finite answer. And that answer has, sorry.
Again, what is U? It should only respect J, nothing with the...
So there's a J there, and there's a J here in the background. And so the D of U needs to commute with a J. So that's another, we call it pseudo-holomorphic or J-holomorphic because the J on the target is not necessarily an honest complex structure. If it was, then it's just a holomorphic map. Okay, and so if we cook up the constraints properly, we get a zero-dimensional solution set, and then we can ask how many elements there are. And the question has two parts to it. One is we want to pose the question so that the answer will not depend on choices we made. So for example, if I take one of those constraints pi and I want to vary it within its homology class, I want to be still getting the same answer. I don't want the answer to depend strongly on the conditions I put. And secondly, well, if there is a number, I want to know what it is. So there is a question of can you in principle compute those numbers? And then if you can, then can you actually compute them to the point where you give me explicit values? And, okay. And the way we might want to approach this problem is by considering moduli spaces of holomorphic maps with marked points. So we consider all pseudoholomorphic maps from the sphere to the target manifold. With marked point on the sphere, they need to be distinct from one another. We fix the degree, of course, and mod out by reparametrization. So if the map lands the same place and the marked points land in the same place, you don't want to count them as separate, so you mod out by reparametrization. And you have to compactify it, because if you want to count elements of a space, it better be a compact space. The compactification is what we call Gromov compactification. So one thing that can happen to a sphere, to a sequence of spheres, is that a certain region in the sphere will develop much faster than the rest of the sphere. And so in the limit, what you get is what we call a nodal surface, is when we have two spheres with identified, where one point on one sphere is identified with a point on the other sphere. That's a nodal curve, and so we want to take this type of creatures also as domains of pseudoholomorphic maps. So a typical element in the moduli space can look like a map from a sphere, can look like a map from a nodal curve with one node, and of course this bubbling thing, this thing that we call bubbling, this creation of nodes, can happen in more than one place. And as long as the total degree adds up to the same beta, they would all be possible domains in the moduli space. Okay, now we have this lovely moduli space. We can rephrase the problem of counting curves with constraints. We say, well, now what we want is elements of this moduli space of maps with marked points, so that the marked points are mapped into fixed constraints. So one way of writing it down is by writing an integral. Now, if you're not comfortable with differential forms, no worries. All I want you to take from this expression is that it's some integral over that moduli space. So if you are comfortable with differential forms, I will elaborate a little bit. You take your constraints, you pull them back via evaluation maps to the moduli space. This gives you a chain in the moduli space that represents all maps whose marked points satisfy the given constraints. And then you want to sum all this up, so you just take the integral. But the upshot of this slide is that if you want to one natural way of rephrasing the problem of counting curves with constraints is by writing an integral that has of something that has to do with the constraints, an integral over the moduli space of curves with marked points. Sorry, maps with marked points. Indeed, this strategy works well. So as long as the moduli space is nice enough, so you need to have, say, differential forms to write that integral. You need the moduli space to be smooth in some sense to write this integral. You can use this expression, and it defines invariants that are actually invariant under changes such as variation of a constraint within a homology class. Computing these invariants is generally very hard, but sometimes you can compute them using a cute gadget called WDVV equations. Well, cute gadget is an understatement here, but yeah, it's an interesting creature that can be used, among other things, to compute invariance. And I will talk about this WDVV a little bit later in more length, as promised. Now I want to play the analogous game in the open theory. So again, we want to, our universe is again a symplectic manifold with an almost complex structure. In addition, we have a Lagrangian submanifold. So that's a submanifold of half the dimension that plays nicely with omega. And the baby example I want you to keep in mind is, again, the projective space. The complex projective space and the real projective space is a Lagrangian submanifold within the complex projective space. For the purposes of my work, we also want the Lagrangian to be oriented. So in particular, in the projective case, you can only take odds values of n, because otherwise RPN is not oriented. And relatively spin just means that the moduli spaces are also oriented. And the basic question that we have, that we want to answer is, again, we have maps from, now we have a genus 0 surface with boundary, so that's just a disk. We want to map count pseudoholomorphic maps from a disk to the ambient manifold so that their boundary lies in the Lagrangian submanifold. Again, in order to get an answer that's a finite number, you want to fix the degree. Now it's a relative map, so the degree will also be in relative homology. And we want to add marked points at the interior or at the boundary. There are two substantially different types of marked points now. And the marked points at the interior will be constrained to lie in submanifolds of the ambient manifold, and the marked points at the boundary should map to some constraints that are contained in the Lagrangian. Again, if we cook up the dimensions of the constraints properly, we should hope that we get a finite answer. And we want to answer the question of how, to answer the question of how many such maps there are, we need to define the count invariantly, and we need to be able to compute explicit values. We would attempt the same thing we did before by using a moduli space of disks now with marked points. We have maps from the disk to the manifold with boundary conditions in L. We have now two types of marked points at the boundary, marked points at the interior. Again, a fixed degree, mod out by reparametrization, compactify, and we want to write the expected value of the Gromov-Witten invariant as an integral of some expression over this moduli space. Now here begins the place where the open Gromov-Witten theory substantially diverges from the closed one, is because the compactification is very much different. One thing that can happen in open theory, which obviously does not happen in closed theory, is if this, well, you will remember we had the situation where some region would develop too fast and it will bubble off. Now here it might happen near the boundary, in which case the limit nodal curve is two disks with an identified point at the boundary. This in addition to the situation where we had spheres bubbling off in the closed theory. Another thing that can happen in the open theory, if there's no marked points in the boundary, that is, the boundary can shrink to a point. And this is also something that's unique to the open theory. Obviously, you start out with something with boundary, and you end up with something, well, I guess with the generated boundary, you can say. So the types of elements we will have in this moduli space will involve disks on the open set, but to compactify, you will have to add disks with nodes that can be real, or can be at boundary points or at interior points. Can happen in more than one place. As long as the total degree adds up to our initial required degree, those configurations also contribute. And also now we have this situation where the boundary degenerates to a point. Of course, this does not always happen. This only happens if we don't have any marked points on the boundary. And also the class needs to be contractible in L, of course. Otherwise, well, it doesn't contract. Still, I mean, you can argue that it kind of looks similar to the picture we had in the closed theory. So why is it so much different? Why does it make things more complicated? Well, if you have bubbling at an interior point, then the node you get here is essentially a complex node. So the space within which it lives in the moduli space has complex codimension 1, so real codimension 2. Contrariwise, if you have a boundary node, well, that will now have real codimension 1. This degeneration is a slightly, maybe more confusing calculation, but it also has real codimension 1. And so now the moduli space has boundaries. So if you were to define invariance using this integral, because the boundary is not empty, there is no reason to expect the integral to be invariant under changes. More explicitly, if you were to take a different representative, say, then the difference will be an integral of something exact, but the difference of the integral of an exact thing over something with boundaries is not generally zero. It's something that depends on the boundary. So the codimensional one boundary, so the boundary of the disks creates boundary in the moduli space, which then disrupts invariance and makes life harder for everybody, but also more interesting. So people have been thinking about this and have defined open Gromov-Witten invariance in several cases. So for example, if there is a certain symmetry, so an S1 action or a real action, you will notice that the type of constraints you can put on the boundary is either no constraints or point constraints, even when invariants are defined with the addition of this real structure. If for Calabi-Yau threefolds, there is a different approach that's more closely related to ours. Well, in that context, again, like having point constraints is a little bit irrelevant. So the pool of cases when open Gromov-Witten invariants are defined a priori is rather small. And when it is defined, it seems that boundary constraints are very limited in what they can be. So it would be helpful to understand that. It would be helpful to understand, and it would be helpful to get rid of conditions that are not essentially symplectic. Like we don't really, Gromov-Witten theory should be symplectic. It should not be real. In some sense, I guess. Some people would strongly disagree. Anyway, so I will just mention also, since we are talking about previous results, I will also mention results about WDVV, which again I will go back to later, but for now you can think about it as a computational tool. All work so far about WDVV have been done only in the real setting, so when there is an antisymplectic involution. Think complex manifolds, Kähler manifolds, dimension 2, in dimension 3, and in general odd dimensions if you don't have boundary constraints. So basically, the real cases where invariants were defined before, they were also proved to satisfy WDVV equation. Otherwise, tough. Well, yes, and then the non-real cases, there is no WDVV so far. So our approach, I will talk mostly about the definition, but also a little bit about the WDVV, and you will see how somehow it sort of works well together, hopefully. So we want to deal with boundary phenomena, which is disk bubbling and boundary degeneration. And we deal with each of them not by using symmetries, but by using considerations that are largely topological in nature. So for disk bubbling, we cancel it out by using a bounding chain, which I will literally be talking about in the next slide. And for the sphere bubbling, we will be incorporating spheres, which I will be talking about after we talk about bounding chains. So
when you say cancel out,
yep.
Do you mean you construct a moduli space without boundary, or you mean the contribution is canceled out by some other contribution?
Well, it's more like the latter. It's like you would say. It's not an honest canceling. Like in the case of spheres, I guess you could say it's like basically you cancel out two different contributions.
So like the moduli space has the codimension one boundary, but
but you manage to count those when you count them all together somehow, those different boundaries. Okay, so it cancels out in the sense that you end up having something with no boundary. Sort of that's the picture in the background, is that you combine those different moduli spaces so that together, in a sense, they don't have boundary. I do not really want to say it this way because...
No, that's fine, but the point is...
Because it's not correct, but yeah.
The point, though, is that you prove invariance of this construction?
Yeah,
Okay.
yeah.
You have many modular spaces and they are related in some ways, so there's more structure to the problem than you might think.
Right. So you do, like, the point is you do have to consider a lot of moduli spaces simultaneously, and then the end result is invariant. Yeah. Thank you. Okay. So a bounding chain that's designed to deal with disk bubbling is a special type of boundary constraint. So in particular, if we have to take constraints in a boundary constraint, this in a bounding chain, this will explain why the options for boundary constraints before were very limited. And the reason sort of behind that was not just an accident, but it was because those were the bounding chains in that context. So geometrically, it's designed to keep track of disk bubbling, and algebraically, it's an element, it's a Maurer-Cartan element, so it satisfies a fancy equation. Let me tell you about this equation a little bit more so that you at least see what kind of connection there is between the bounding chain and those disk bubbling. So we have those operations on, I'm writing everything in differential form language, but again, if you're uncomfortable with differential forms, feel free to think just submanifolds of L. It's an operation that eats submanifolds of L and spits out a submanifold of L. So what it eats is eats those alphas. It eats the constraints that you impose on marked points on the disk. And what it spits out is a point on the boundary of a disk that satisfies those constraints. So other way of thinking about it is just the boundaries of all disks that satisfy given constraints. So this is, in particular, this is a submanifold of L. And in the special case of k equals 1, we also have to add a correction, which is just the boundary of the one input constraint that we have. It's a little bit, I guess, obscure. It's designed to satisfy infinity relations. So it makes differential forms in L and infinity algebra, which is useful to those of you who like infinity algebras or floor theory, or as I'm trying to advocate, Gromov-Witten theory as well. And then the Maurer-Cartan equation, let me, for simplicity, take equals 0. Before, you might remember it was equals c times 1. For simplicity's sake, let's take it equals 0. What does it mean then in the picture? It's boundaries of disks with constraints in B, right? Because that's what MK do, is they spit out boundaries of disks with constraints in the input. And then in the special case, when k equals 1, it also spits out the boundary of the input. And I'm ignoring signs all over the place because signs are horrid. And if you do ignore signs, then what this equation tells you is the two are the same. The boundary of a bounding chain is the same as boundaries of disks with constraints in the bounding chain. So B is a bounding chain if it solves this equation, if it satisfies this property of being related, of its boundary being related to boundaries of disks. So we started out with the problem where we had extra disks to get rid of. We added a bounding chain, a special constraint, that now adds another type of boundary. We had a problem with one piece of boundary. We created even more boundary. And miraculously, that piece was nicely designed exactly to balance out the problematic boundary. It's a classic example where more is actually more. So.
Some sum over degrees somewhere?
Well, the MKs incorporate all degrees, yes. So you'll have sum over degrees. And in general, you might also want to add bulk deformation. So interior constraints. You can do the whole picture. You can also add interior constraints all over the place. And yeah. So this B is quite complicated. It involves all sorts of degrees, and it will also, obviously, you need to you sum over all numbers of boundary insertions as well. So. But it does the job. So if we want to, so in order to define, I will not give the full definition because the notation will be horrid as well. And so, but the idea here is if we take all those disks with constraints in B, we also had this output point. We want that also to lie in B. So we take just literally all the constraints of the disk to just lie in B. And we sum over all those contributions, we should get something that's invariant under change of data. So this B really does do the job. We obtain a generating function, a function that we use as a generating function. It's invariant under gauge equivalence. Gauge equivalence is an equivalence relation on algebras, but it reflects certain equivalences that you have in the real world. So for example, if you were to change your constraints within cohomology class, algebraically this translates to gauge equivalence. So it is invariant also in the naive sense that we wanted before, that you can change your data and get the same numbers in the end. So we can do that. In the special case, I have a feeling like I'm going too fast here. Do you like? Is there anything I can say to make it easier? Is there any question you can ask to help me help everybody else? Okay. Well, these bounding chains, as we have remarked, are quite.
Do such B's exist?
Yes, it's an excellent question. And in general, there's no like general theorem that says B's always exist. But basically, in any interesting case, they do seem to exist. And moreover, in some cases, we have a good understanding of what they are. So from Gromov-Witten theory perspective, an interesting case is where L is a rational homology sphere. When it only has real cohomology in 0 and top degree, then we have a full understanding of those bounding chains. In fact, they are classified by the value of their integral on the Lagrangian. So in other words, you can write them as something that represents a point. Right, the only part that contributes to the integral of B over the Lagrangian is the degree n part of it. So it's just the point. And then to that, you will generally have to add corrections that are not closed that come from this Maurer-Cartan equation. But the bottom line is, all those B's just look like a multiple of a point, plus those corrections that are not closed that come from the Maurer-Cartan equation. Right, they're not closed in the sense that they have a non-trivial boundary. The non-trivial boundary, we know exactly what it is. Being a bounding chain means that their boundary is the boundary of other disks. And so in that sense, when you take those B's as inputs for your generating function, what you get in the end of the day is invariants that count configurations of disks with point constraints. And let me illustrate. If you were to count, say, invariants of degree beta, with 3 marked points on the boundary that are restricted to be mapped to points. So those are the constraints I impose on those marked points. One possible contribution is, of course, if you have a disk that genuinely satisfies it, you want to count it. But another type of creature you might want to count is configurations of disks that together add up to those constraints. So beta 1 plus beta 2 plus beta 3 add up to beta. And the total number of marked points that are constrained to lie on a point is 3, just like there. We want to count this configuration as well. We don't want to just randomly count all possible combinations. We need the bounding chain to tell us which configurations are relevant to our count. This is the non-closed part. This blue thingy is the non-closed part that tells us which configurations we need. But in the end of the day, what we count is configurations of disks that collectively satisfy the constraints we put upon in the enumerative problem.
Sorry.
Yep.
I'm confused why beta 1 plus beta 2 plus beta 3 equals beta. For example, there's a different number of mark points.
There's different. No, beta is the degree of the disk. Beta is the degree of the disk. So if this is a degree beta disk, and these 3 add up to degree beta as well, then it satisfies the degree part of the requirement. And now the marked points, so you have here the marked points that are constrained to lie on a point. That's the same as here. And then, yeah. And then in addition to that, you will also have marked points that sort of don't count because they just tell you how to connect the dots, sort of how to connect the spheres. How do you know who to count and who not to count?
That's good. I got confused when it's beta 2 plus beta 3.
There. Yeah. Oh, that's my evil genius. No, so what happened, like the idea here is that somehow the B, what the B is trying to tell you is trying to tell you, well, these two are connected not by accident, but they are connected because they used they used to live in the boundary of a bigger disk. Okay, so the way you see this in the picture, for example, is think of this blue B as a trace of a boundary. Okay, as the disk proceeds. And so when you reach this point, you see that there used to be a configuration where they participated as there's a nodal curve there that lives in the boundary of something bigger. And so that's how you kind of know that you want to keep track of that. So this gives you the before picture. This gives you the after picture. Like before they collided, and this gives you the picture after they collided. And this can subsequently like split down even more. But what the bounding chain is telling you is that, well, notice that these two used to be in the boundary of something bigger. It's really cool if you write it down, it's actually what it says.
On the right-hand side, how many pictures are there?
Sorry. On the right-hand side,
I think B is the bounding cochain.
yes, B is the bounding cochain, which I'm calling chain in this talk because I'm lazy. Yes.
So like that whole thing is a picture of B.
No. So only the blue part is a picture of B. This whole picture is like, in the end of the day, how do you know who you count? So this is one contribution to the total count, is because if you have a configuration of disks here, you need to sort of include the before and the after picture, but one configuration. So I know what might help. If you're thinking about you have those disks and you have where the output point is, right? The 0 point, the output point. Like here you would have. No, that's not answering your question. So here, well, like what I'm trying to say is. There's a what?
Where does this picture live in?
So, so the blue part lives inside of L, the Lagrangian. This and that lives inside the Lagrangian. The boundaries of the disks live inside the Lagrangian. The inside of the disk lives somewhere. And then what I want to count here is this disk with constraints in this whole business. And the reason I want to count it is because it came from bubbling. But what I count is this disk with a constraint, with a fancy constraint. Okay? I can draw more convincing pictures later if you want. Okay. So far, I told you how we deal with the bubbling part. There's another part, is when the boundary degenerates to a point. Another way we think about it is, well, you can think about it as a disk with a degenerating boundary, or you can think about it as a sphere that intersects the Lagrangian. And so that's how, by incorporating spheres into our count, we can balance out this degeneration part. We can cancel out those contributions. Algebraically, the way we incorporate those spheres is by using the mapping cone. So again, those of you who are more comfortable with differential forms, it's just integration over the Lagrangian. But regardless, it's something that eats chains in the ambient manifold, and it spits out numbers, spits out scalars, given just by integration over L. So if you will, just intersection. How does this chain in X intersect L? The cone complex is a chain complex. I have shifted degrees here for the degrees to work out, but just ignore it. It has nothing to do with the picture. The cone complex is just, on the complex level, is just a direct sum of the domain and the range. And it has a fancy differential, but the point is that it combines information we get in X with information, with data we get in L. So for example, this generating function was just an element in the coefficient ring. So this is some information about disks that we have that lives here. We can combine this now with information we get from X. So the strategy to deal, to define those things is, well, let's find first of all something that's invariant in the cone, or rather in the cohomology of the cone, and then project this back to the coefficient ring so that we get back some data that has to give us back information. In the end of the day, we want numbers, we want information about the disks. So we start with something that's invariant in the cone, and then we project it. And the reason it's not just, you cannot just forget the X part, because the projection as is not a chain map. If you want something invariant, you need to find a clever way of projecting it so it is a chain map. And so but the way you do it is exactly by incorporating contributions from X into your projection. So you take the second component, which gives you back the data you had about disks, and adds to that information about spheres. And it works. We still need a bounding chain in the background because we still have disk bubbling as well. But you can now use this process to create open Gromov-Witten invariants that are a refinement of the invariants we had before. So before that, if we had 0 marked points and the boundary was collapsible, we had to put the invariance to be 0 because we couldn't deal with boundary degeneration using just the bounding chains. Now that we found a way to incorporate spheres, we can get possibly non-trivial values. And of course, whenever we didn't have the problem of boundary shrinking, we get the same invariance as we had before. So this is a refinement that comes from adding contributions of spheres via the mapping cone. OK. So that as pertains to definition. So in that sense, I want to say, kind of answer the first half of the question, can I count curves with boundary? The answer is substantially yes. Can I count them? Can I really count them? Well, what can you do in closed theory? In closed theory, you have this equation. Let's say we have a generating function of a closed Gromov-Witten invariance. We find that it satisfies a PDE that's useful for computations. So let me give you a picture for what this PDE is trying to say. Right? It's just derivatives of the generating function. Taking a derivative of a generating function, ignore the grayed out parts for a second. Taking a derivative of a generating function of spheres is the same as taking spheres with constraints in the directions in which you take the derivative of. So what the left-hand side here is saying is, let's take all spheres with constraints in u and v, and this is this part. Let's take also all spheres with constraints in w and y, and this is this sphere. And the grayed out part is just a fancy way of saying this sphere is intersecting the other sphere. And so in total, what the left-hand side of the w dv tells you is we consider all those configurations of a nodal curve where we have just two spheres intersecting. One of the spheres has constraints in u and v. The other sphere has constraints in w and y. The other side tells you exactly the same thing, except you flip the v and the w. And the claim is that those contributions equal the other contributions. And the way you might go about proving that is by finding a homotopy between one configuration and the other configuration. If they are homotopic, then in particular the count is the same count. So we want those to sort of live in the boundary of something with the homotopy between them. And indeed, we can find the homotopy like that by considering just one sphere. And what happens to this sphere if we impose four marked points to lie to have real cross ratio? So if you will, lie on a geodesic, I guess, is the analog of that. Well, what are the boundary phenomena that happen in this situation? Well, the marked point that will go to V can move around along this line, right? Only along this line, because we cannot disturb the cross ratio. In the limit, it can try to collide with U. Now, we need the points to be distinct. If things collide, it's the same as saying, like we had before in the picture, if things develop too fast in a smaller region, they bubble off. If V collides with U, they bubble off in a sphere, and we are left with a sphere with W and Y, and a sphere with U and V bubbling off. What happens if V collides with U? If V collides with Y, we get the same thing, V and Y bubble off, and we remain with a sphere with U and W. And so by considering this moduli space and what happens when points move along the geodesic, we can prove the WDVV equation. And it's highly non-trivial. And in a paper from '94 by Kontsevich-Manin, they use it to produce recursion equations. In particular, for CP2, they use those recursions to compute, to prove that they can compute all the invariants, and they give some sample numbers. So in CP2, there are not that many constraints you could take in principle, right? Because, well, you only have basically points. So if you know the degree, you know exactly how many, what the other constraints are. They are just 3D minus 1 points, and you have all those nice numbers. There's one line through 2 points, right? The number of lines through 2 points is 1, which is kind of what you expect. And the rest sort of follows from the recursion process that they offer there. So it's nice. You can sometimes use it for explicit calculations. In the open setting, we want to play the same game. And we do. So now we get a PD that involves disk invariance, sphere invariance, and also this Maurer-Cartan constant that we had in the Maurer-Cartan equation, but don't get upset because we can rephrase those equations in a way that avoids using the Maurer-Cartan constant if you're not happy with it. So yeah, literally the only difference between this and that is that this one has bars over the omega. So what does this equation mean? So similarly to what we had in the closed case, right? We started with a sphere and moved around constraints along the boundary. We can try to do the same thing with a disk now. We have a geodesic. And well, now we only need like 3 marked points on the geodesic are already non-trivial. And we can try to move this middle point, this W, and see what happens when it collides with U, see what happens when it collides with V. When it collides with U, we get bubbles, right? They bubble off. If they collide at the interior, they bubble off in a sphere, sorry. But they can also, both of them, go very rapidly towards the boundary, in which case they bubble off on a disk. So both of these contributions will happen on one side of the equation where U collides with W. And then the opposite happens when W collides with V. So the picture here is exactly that. We have a sphere with constraints in V and W, and a disk with a constraint in U. And this grayed out part tells you that they intersect in an interior point. And then we have a disk here with constraints in V and W, and a disk there with a constraint in U. You will notice that I lost the geodesic here, seemingly unfairly, but it's the magic of A-infinity algebras, or more specifically, it's the magic of the unit property, is that we can trade this geodesic for an extra constraint here on the boundary of the disk. So we don't need this Gij thingy to say they intersect. Instead, we just sort of use algebraic properties of differential forms on L, basically. And this gives you the right-hand side is the same with U and V flipped, hopefully. Yep, okay.
What is that S?
So that S is a parameter associated with the point part of the bounding chain. So in the case where, in the sphere case like we had before, for example, the bounding chain is just a point plus stuff. So that point will have a parameter associated with it. More generally, the point part still plays a special role, but it's like, for the sake of picture, you can just think about the sphere case where you have all those variables associated with the constraints you put on, right? Because what's a generating function? It's a function in formal variables And if you take, and each formal variable is associated with a type of constraint you might impose on the curve. And so for interior constraints, you need formal variables. For the boundary constraints, you need formal variables. So S is just a formal variable that's associated to the boundary constraint. A very special case is the projective space. I should have specified odd n, sorry. Because again, I want the Lagrangian oriented. But for CPN, we can produce, we use this WDV equation to write recursion formulas, and so produce very explicit values, very explicit. So definitely in this case, we can really count them. This table only gives examples of invariance with boundary constraints, no interior constraints, but of course you can also add interior constraints, no problem. It's just a lot easier to make a one-dimensional table when you don't. Sorry, a two-dimensional table. One-dimensional will be boring.
Sorry.
Yep.
Why can't the number of boundary points, it looks like you can't get all of them? Why can't you have like 3 and 7?
You can, but it's like 0 for degree reasons. It's just not interesting. Yeah, these are just the non-zero values. The first non-zero values.
Can I ask how you use your equation? Because your equation has like 2 things on one side and 2 things on the other side.
Yep.
Do you like move, is it like 1 thing and then 3 things? Is that how you use the
Yep. Well, sometimes it's in 4 things because the one thing can also contribute something in lower degree. So we move that. But yeah, in principle, it's 1 thing and 3 things. Yep. So we're done with CPN, and we're back to talking about the WDVV equation from a different perspective. I know it's a lot to take in, but now is like a really good time to tune back in for all those of you who have spaced out so far. Quantum product is just a product on cohomology of X. Well, obviously it's a product, so it has 2 inputs, and it spits out the locus of points on the sphere that satisfy those 2 constraints. So we're thinking here about, again, elements of the cohomology as constraints to impose on a sphere. So if we have a sphere that has 2 marked points, 1 constraint to line U, 1 constraint to line W, we want to see where other points of the sphere can happen. Let's consider the associativity of this thing. So what would it look like? So we take a product of 2 things, and then we multiply it with another thing. A product of 2 things is just this, right? U times W is when you look where a sphere occurs that satisfies the constraints in U and W. Taking a product with V is just saying we have a sphere with a constraint in V and a constraint in this other thing, and we see where points of that sphere can happen. Okay, so similarly, if we take U times something, so U times something is output of spheres with constraint in U and another constraint in something. The something happens to be a product of V and W. And you will notice that it starts to look very similar to the WDVV picture we had before. And the reason is because it's basically the same thing, except we need to impose a constraint on the extra point, and then we get exactly the same picture as we had for the WDVV. And so the WDVV is not just a computational tool, it's actually a way to express an algebraic property of something that happens on the cohomology of X. The WDVV is equivalent to the associativity of this product. Now I want to play the same game in the open theory, and the open creature that would be parallel to that is on relative cohomology. This is mem. We ran out of letters, so we used mem. Mem is a Hebrew letter, stands for machpelah, which is product. So for the simplicity of the picture, rather than talking about relative cohomology, I want to talk about the cone. And the reason I can do this is because the cone is is strongly associated to the relative cohomology. So if you were to take all your coefficients and just the real numbers, then the cone gives you the exact same cohomology as the relative cohomology. And so what I want to do instead is sort of look at a version of this product mem on the cohomology of the cone. And so what I need to tell you in order to tell you what mem does, I will need to now tell you what would be the output. The input will be generally pairs, something in X and a number, something in X and a number. And the output will also be a pair, something in X and a number. And again, for the simplicity of the picture, I will take the number in one of them to be 0, and the definition of mem just says, well, in the first component, you have something in X and something in X. We know how to take their product. It's just the quantum product, the usual quantum product, is we take spheres with constraints in U, constraint in W, and we see where the output goes. Like where the points can be of a sphere. In the second component, we need a constant. So one contribution of this constant will be, well, let's sum up all the disks with constraints in those U and W. And another contribution of this thing will be C is again this Maurer-Cartan constant. You don't need to actually know what it is. Just believe me. Just believe the formula is just some multiple of the non-trivial constant we may have here. So in particular, if A is 0, then this part is just 0, and you just have spheres and a disk. And it's kind of what you would expect. The whole picture is kind of schematic because, again, those disks are not really disks. There are configurations of disks and all this stuff. But OK, what would be the associativity of this thing? So let's take a product and then multiply it again with a third input. Because it gets a little bit confusing, I made it. OK, so in the first component, we know exactly what it is. In the first component, this is just a quantum product, and this is again the quantum product. So what we get is exactly the same picture, literally the same picture. It's copy-pasted from the other slide. In the second component is a bit more interesting, but also a little bit more confusing. So that's why I put a cheat sheet. Well, what happens? The one contribution is a disk with constraints in the two things we had before. So the output here needs to be a disk with constraint in V and a constraint in the closed part of mem UW. So this is the V, and this is the closed part of mem UW. OK, this is the closed part of mem UW. And it goes as a second constraint on the disk. This will be a disk with one constraint in V and one constraint in this thing. I say thing so much, I feel like I'm in the Addams Family thing or something. OK, and the other contribution is this Maurer-Cartan constant times whatever we had in the open part. So this is what we had in the open part. And so this is sort of, again, you will notice that it looks a lot like the WDVV equation. Well, up to signs, but I'm ignoring signs all over the place, so you'll forgive me for that. This is sort of one of the reasons why I like the version of the WDVV that maintains the C. But again, you can translate this into something in just omegas or just omega bars. And so what we get, again, is the WDVV is equivalent. The open WDVV is equivalent to saying that this product mem is associative. And of course, I mean, you kind of, OK, I'm sweeping stuff under the rug, but that's kind of the point because it's a colloquium talk, and yeah. Back to the original question. So in general, you can kind of count curves with boundary, at least genus 0. But counting them to the point where you get numbers is more complex. Sometimes you can, sometimes you cannot.
Sorry.
Yep.
About numbers. So for Pn, you computed them?
Yeah, so for CPN, they're all computable.
For like which other targets are they computable in the really sense?
So it's kind of, it's a recent work, really. So there's not much work done. In dimension 3, there's this work by Chen Zinger where they do real symplectic manifolds in complex dimension 3, and they give computations for CP3. They give computations for the threefold product of P1. Explicit, like with numbers and everything. It's pretty cool. And I know that Nick Sheridan has a student that does some computations for the quadric surface, I think.
So is it basically like in the Fano case, sort of in the Claviau, or?
So the type, yes. So the type of result you would expect would be parallel to the closed result. So yes, we would expect it to be Fano, and you might need like a finite set of generators or something. It's basically a Kontsevich-Manin version of that. Yeah. And I'll stop here.